Okay. So with 4.3, we're getting a little more in-depth with logarithms, and we're going to look at rules of logarithmic functions. So you know how exponential functions have rules? We've got the product rule, quotient rule, power rule. There's actually a bunch of different power rules. So we're actually taking all of these rules from the exponential functions and applying them on our logarithmic functions. So as you will notice, again, we've got the product rule. We'll also be looking at the quotient rule, the power rule for logarithms, and a couple more into that. So let's start out with our product rule for exponents. Now remember, the idea with product rule for exponents is if you're multiplying the same base, so here we've got 2 to the third being multiplied by 2 to the second, we always end up adding our exponent. So 3 plus 2 gives us 5, and you end up getting 2 to the fifth. So using that same idea of when it's product rule and we end up adding our exponents, the rule for logarithms ends up actually being if you have a number and they're actually just using these values from here. So if you've got 8 times 4, which would of course be a number 32, but we can break that number down and you end up using addition to split up something that's being multiplied. So product rule for exponents says if I'm multiplying 2 bases, I add my exponents. That's the same kind of thing that's happening with logarithmic rules. If I have a value that can be split up by multiplication, I can write them as 2 separate logs by using addition. So multiplication leads to addition, and of course, they will still end up having that same base A. You have to make sure your bases are going to be the same. So we're basically saying the logarithm of a product of 2 numbers, so that's this right here, is equal to the sum of their logarithms. So just to kind of see how this rule comes into play, we'll look at 2 different types of examples here. They're giving us 2 separate logarithms, and they're asking us to combine it into a single log. This one here is giving us a single log, and they're saying either use addition or subtraction to write them as multiple different logarithms. So let's take a look at this product rule here for logarithms. Okay, so product rule for our logarithms. Now this first question is giving us log of 5 plus log of 3, and they're asking us to rewrite it as a single log. Don't just assume that your bases are the same. Always make sure that the bases are in fact the same, because the only way I can combine this is if both my logs have the same base. So this is of course base 10. This is also base 10. If your bases match, then yes, we can convert them into a single log. So we're actually given the right-hand side of our rule, and we're combining it into a single log. So since this is addition, product rule for logarithm tells us that we can use multiplication to combine them into a single log. So you're actually taking log of 5 times 3. 5 times 3 gives us what? There you go. So, obviously, if they had asked you to rewrite this as a multiple log, we would have taken 15, broken it up into 5 times 3, and gone the other way and made it into 2 separate logs. Obviously, that's the same thing that's happening on number 2. We are given log of x minus 1 with base 2. And to that, we are adding log of x with base 2. So again, we're combining this into a single log. First thing to make sure is our bases are the same. So they're both base 2. So using our product rule for logarithms, we can go ahead and multiply. And actually, I think I'm going to use a bracket here. I am going to take my x minus 1 and multiply it with my x. Okay. Now, since x minus 1 is one single quantity, when you try to multiply this, make sure that you are distributing that x inside x minus 1, which will end up giving us what?
X squared minus 1x.
Yeah. Yeah, so we end up doing x times x, which is x squared, minus 1 times x, which is x. You just multiply and you get log of x squared minus x with base 2. So this was taking two separate logs, which were separated by the plus sign or the addition, and to combine them, we use multiplication. That's what our little product rule for logarithms is talking about. But for the second type of question, which is saying rewrite each expression using sum and or difference of multiples of log. So of course we can see this is 3 times x. That's our product rule. So it's 3 times x, which means we use the addition sign to separate them. Okay, so for number 3, this is again a logarithm with base 2 of 3x using our product rule. Separate those two and then use the plus sign to separate your logarithms. So it will become log of 3 with base 2 plus log of x with base 2. So multiplication goes with addition. Okay, that's I think the easiest way to remember, and you can always think about how did rules of exponents work, because they obviously translate very close enough to those rules of exponents. Okay, quotient rule for exponents was if you had the same base and you were dividing those bases, you end up subtracting your exponents. If I have 2 to the 5th divided by 2 to the 2nd, that's the same base 2. So we end up taking 5 minus 2, which is where we get the 3 from, right? So 2 to the 3rd is what it comes out to be. So using that same idea, your logarithm quotient rule is, again, if you have something like log of 32 divided by 4, again, this is base 2. To separate a division, we use subtraction. So that becomes log of 32 with base 2 minus log of 4 with base 2. Again, guys, remember, order is always important, especially when you're using the quotient rule. So 32 is the number on the top, log of 32 goes first. 4 is the number on the bottom, log of 4 goes second. So numerator on the top, numerator as the first one, denominator as the second one. So with quotient rule, the logarithm of a quotient of two numbers is equal to the difference of their logarithm. Same kind of examples here. This one is asking us to write it into single log, and this one is asking us to write it as multiples of logarithms. So let's take a look at example 4 here. Okay, so quotient rule for logarithms. Okay, so looking at number 4, we are given log of 5x minus log of 5. So it's the minus sign. That's of course telling us that we have to use the quotient rule. And again, anytime you're combining these into single logs, make sure your bases are matching on the logarithm. So these are both base 10. Using our quotient rule, write it as just one log. And then the first value goes on the numerator. Second value goes on the denominator. Can we simplify that fraction? Yeah, what can we do?
We can take out the 5s.
Yeah, the 5s will actually end up canceling each other out. You know, anytime you see fractions, simplify them. So you end up actually getting just log of x as your single logarithm. So subtraction goes with division. All right, go ahead and simplify number 5, and let me see what answer you come up with. So that's natural log of x to the 8th minus natural log of x to the 3rd. Jose, what do you have?
I have I just got x to the power 5.
Okay, that's it?
No,
With the natural log, right? Yeah, just make sure the natural log is there. And of course, we know this is the same base because they're both natural logs, so we can combine them into a single logarithm. X to the 8th will go on the top. X to the 3rd will go on the bottom. So this is kind of interesting because you are using both the quotient rule for logarithms combined with the quotient rule for exponents, because again, this is the same base x. You've got 8/3 in your exponents. So 8 minus 3 will give you 5. Like I said, anytime you see a fraction, if you can simplify it, clean it up, make sure you are cleaning it up, and that should be your final answer, natural log of x to the 5th. Okay. Did anybody have a question on number 5? Okay, what do you guys think will happen for number 6? This one is log of x divided by 2. They're asking us to use sum or difference of multiples of logs. Raylan, what do you think will happen?
Log of x minus log of 2.
Yeah, the numerator will become the first logarithm, so log of x, and then minus. Denominator becomes the second logarithm, so that will be log of 2. And of course, there's nothing else we can do to simplify this, so leave it as it is. Log of x minus log of 2. Okay. So product rule, quotient rule. Now the next one we want to look at is of course the power rule. So again, your exponential rule was if I have one base with two different exponents. So I have 2 to the 3rd power, and that whole thing raised to the 2nd power, you actually end up multiplying your exponent. So that means we end up multiplying 3 times 2, which is where that 2 to the 6th power comes from, right? 3 times 2 gives us 6. So what happens with logarithms, you're still multiplying exponents, but it looks a little bit different. So keep in mind a log. So if you are just looking at log of 8 with base 2, this is always going to equal an exponent, right? Because it's basically saying 2 raised to what exponent gives me 8, which is going to be the number 3. So this one is always an exponent. Since I have 8 to the 2nd power, my 2 is also an exponent. What you're really doing is taking this number 2 and bringing it right in front of that logarithm. So you end up getting 2 in front of the log, and then you multiply 2 times log of 8 with base 2. So your power rule is basically the idea, and I don't think this will let me write on it, but you're taking this n and bringing it right in front of its own logarithm. Let me show you that here. So if I have a logarithm m to the power of n with base a, the power rule for logarithms is telling me take this n, which is an exponent, and bring it in front of the logarithm. So that's how you end up getting n times log of m with base a. Okay, so if you look at the examples we have here, they're asking us to rewrite each expression in terms of log of 5 with base a. So they're literally just asking us to clean this up where all of our logarithms are just going to be log of 5 with base a. So how can we rewrite these guys? So this one, of course, is pretty simple. The first one, we've got log of 5/3 with base a. So literally just using our power rule, we can take that number 3, our exponent, and bring it in front of our logarithm. So that will end up giving us 3 times log of 5 with base a. You can actually just write it as 3 log 5. You don't have to write the multiplication symbol. Okay. Product rule, sorry, power rule, where we end up multiplying the exponent with the logarithm itself. Now number 8, they're actually giving us a little fraction in here. You've got log of 1/5 with base a, right? And they only want the answers as log of 5, not 1/5. So that means we need to clean this up. So since that's a fraction 1/5, we're actually going to start by using our quotient rule for logarithms, which would then mean we end up getting log of 1 minus log of 5, right? Both with base a. Now what's log of 1? We had talked about this earlier in section 4.2. Just in your calculators, type in log of 1 or natural log of 1. What do you get? 0. Log of 1, any base, is always going to be 0 because the idea is a raised to what exponent gives us 1? Well, a raised to 0 gives us 1, right? So you're actually always going to get 0 for log of 1 no matter what the base is, minus log of 5. So you end up getting negative log of 5 with base a as your answer. So here we're using quotient rule actually to help us simplify. Now if you wanted to use power rule, you can rewrite that 1/5 as 5 to the power of -1, and if you bring that -1 to the front, you end up getting same answer. So you can use quotient rule or power rule to simplify this one. All right, what do you guys think is going to happen on number 9? Log of square root of 5 with base a. And they want us to just write it as log of 5 with base a. So how do I rewrite that square root of 5? One of the examples we just did a little while ago had 3 to the power of 1/2, which became square root of 3. That's something you need to remember, okay? Rewriting radicals as exponentials is something you should really be comfortable with. To rewrite that square root of 5 as 5 to the power of 1/2, and then again using that power rule, bring that 1/2 to the front. Okay. Log of square root of 5 with base a will become 1/2 log of 5 with base a. Questions on these 3 examples? So product rule, quotient rule, power rule. Okay, these will be three of the main ones, but then we actually also have inverse rules. And inverse rules actually work with what happens if we take a composition between exponential and logarithmic functions. And this was, I think, back in, again, I think it was section 2.5 where we discussed inverse functions the first time. Anytime you take a composition between two inverse functions, you always end up getting x as your answer. And you can look at, I think these were the rules. This is how we had mentioned it. So if I take a composition between g of f or f of g, we always end up getting x as the answer. So this is actually true for exponential and logarithmic functions also. So if I take a logarithm with an exponential function inside of it, basically since my bases are going to be the same, log also has base a, my exponential function also has base a, whatever is the exponent, that ends up becoming my answer, okay? And we had actually used this property when we did that, how long does it take $4 to grow to $12 example. That's the same idea we used there. Now, if I reverse that and I have a as my exponential function raised to the power of log of, again, base a, so the log is now my exponent. Same thing is happening here. This base a for the exponential function is canceling out this base a for the logarithmic function. So these guys are canceling each other out, leaving behind that x as our answer again. And these properties really, really come in handy when we're solving application problems for one or the other format of these examples. So these are just generic examples here. We're trying to use these properties to find out what the answer will be. So using those inverse rules, okay, so either you have the log with the exponent or the exponent with the log. So for example 10, we are given base e raised to the power of natural log of square root of 1. This is base e, natural log again has base e, right? So that means we're actually looking at the second part of our inverse rules. So these bases are canceling each other out, leaving us behind with just whatever you had that natural log at, square root of 1. So what does 11 tell us? What will this answer be for number 11?
Y plus 1.
Yeah, because again, my logarithm is a common log. That's base 10. This exponential also has a base 10. So the log and the base 10 are basically, again, canceling each other out, leaving us behind with just the exponent, which is y plus 1. For number 12, you have 7 raised to the power of log base 7 at a value of 999. So what will that guy end up becoming? Yeah, 999, because again, both base 7 cancel each other out, leaving you behind with just a 999. These are basically the same rules, just given to you in terms of any base A or with natural logs, but they are essentially the same thing. Rule 1 and 3 are basically the same thing. If your exponent is raised to number 1, well, the two bases cancel each other out, leaving you behind with whatever the exponent is. If the exponent is 1, the answer is 1. If the exponent is x, the answer is x. Okay. Your rule 5 is the product rule we just talked about. Rule 6 is the quotient rule. And of course, rule 7 is the power rule. So the 3 different rules that we looked at. Rules 3 and 4 are obviously your inverse rules that we just looked at the examples for. As I was mentioning, a log of number 1 at any base is always going to give you 0. So that's rule number 2 over here. Rule number 8 is actually very similar to that example we just did, which was example 8, where you had 1/5. So log of 1 will end up giving you 0. So you just end up with negative log of n with whatever your base will be. So all of these rules, we have looked at them in form of our examples that we have looked at so far. You will need to obviously remember these rules. The rules are not given to you for exams, so just make sure you practice with them, you write them enough that you get comfortable using them. So example 13 and 14 is kind of interesting. They're not just asking us to simplify. They are saying simplify your expression or rewrite them in terms of log of 2 with base a and log of 5 with base a. So they're specifically asking us to rewrite it in terms of these 2 logarithms using, of course, all of these different rules we have looked at. So let's start with number 13. It's given to us as log of 10 with base a. So if they're asking us to use log of 2 and log of 5, how can I break down the number 10? 2 times 5, yeah. So we will actually use the product rule to simplify this guy here, since they're specifically asking us for those logarithms. So using the product rule, what do I do next? Okay, go back and look at rule number 5. With product rule, how can I rewrite that log of 2 times 5?
Log of 2 to the, it's log 2 and then plus log 5, and it's to the
Base A, yeah.
base a. That's the word.
Okay, so log of 2, and remember, multiplication goes with addition, so you use the plus sign to separate these. So you're basically breaking it up into log 2 plus log 5, and always keep the same base as the original logarithm. So it's base A in this case. They didn't really give us a base value. They want us to use the same log 2 and log 5 to break up number 14 also. So they are saying, okay, initially we've got log of 4 over 25 with base A. So where can we start to try and simplify this?
Subtraction.
Okay, subtraction. So that's the quotient rule.
So log base a 4 and minus log base a of 25.
Yeah, so again, denominator will be the second value, numerator is the first value, okay?
And you can actually take that log a to 25. Can you split that into, can you use the rule with the multiplication to split that into 5 as well? Or do you just
Okay, so how would you write it?
so do you log base a to the 5th plus log base a to the 5th, right? Or no? Because it's asking us to write it in terms of log.
3 log a for 3 log base a of 5.
So where are you getting the 3 from?
Are you taking it in like exponential? Oh no, sorry, 2 is what I meant. Like 2 log a.
Yeah, so actually convert the 4 and the 25 into your perfect square. So you can actually get 4 as 2 times 2, or basically 2 to the 2nd power. And you know, we're trying to keep our steps to a minimum. Now you actually have, I mean, a bunch of different ways you can do this. You can break this down into 2 times 2 and 5 times 5 and then use the product rule again. You can obviously go the power rule form that we are going, and then of course you could have also done 2 over 5 initially to the second power, so you could have broken this down first. So there's so many different ways to go about this that not everyone will have the same process. What I'm trying to do here is just keep our steps to a minimum, but once you guys start practicing, obviously feel free to experiment with different processes. Okay. So for each one of these, bring that exponent to the front of their own logarithm. Okay? So that will end up giving you 2 times log of 2, base A, of course, and then 2 times log of 5 with base A. Since both of these guys have that common 2 in the front, you can just bring it outside as a greatest common factor. And again, you can kind of see how my math lab would want you to do. They kind of keep changing the format of their answers on me.
Do you want us to write it that way on the exam, or if we left it to log A?
I mean, even if you got down to this stage, I'll be happy. Okay, so remember, these guys were specifically asking us to break number 13 and 14 down using only log of 2 and log of 5, right? So that's why we're keeping it in this format. Now, these next couple examples are just saying rewrite them using sum or differences of multiples of logs, and then the other set is asking us to write them as single logs. So just depending on what your instructions are, you know, you kind of have to follow what the process is with those. So rewrite them using sum and or differences. So where would you start with log of 3 times square root of x? What rule can we start with first?
Use like split them up, the multiplication. So you just have log 3 plus log of square root of x.
Yeah, so you're starting out with a product rule. So we're taking log of 3 since it's 3 times. That's plus sign to separate them. So log of 3 plus log of square root of x, and we've got one more step to simplify.
Half log there.
Yeah, we do not want to leave that square root on the x. So rewrite that guy as x to the exponent of 1/2 and then bring the 1/2 in the front by using your power rule. Remember, the exponent always comes in front of its own logarithm. Okay. All right. Let me see what you guys can do for number 16. 3 times 2 to the power of x minus 1 That's a good start. Now what will you do with the exponent?
The exponents.
Okay. So very similar to what you guys did with number 15. Start out with the product rule again. So you should have log of 3 plus log of 2 to the power of x minus 1. And then what can we do next? Yeah, take your exponent, that whole x minus 1, and bring it in front of its own logarithm. Now, one thing I want you to be careful about when you're doing this, if you write it just like this, x minus 1 log of 2, it actually looks like you have log of 3 plus x minus log of 2. So to make sure that we know that this guy was your exponent, put that in parentheses. Because since we had a binomial term in our exponent, we want to make sure we know they came together. So put it in parentheses to kind of keep them together. Okay, very good. All right, take another minute and let me see what you guys come up with for 17 and 18. Now you're combining them into single logs. So make sure, obviously you check and make sure the bases are the same before you combine them into a single log. Bless you. So we've got log of x to the 5th with base 7 minus 4 times log of x squared with base 7. They're asking us to write this as a single log. What should our first step be? You're kind of going backwards now, right? So we need to reverse the process. Where would you start?
Won't you take that forward and put it back? So you have to.
Yeah, we got to undo that power rule. So since it's 4 times the logarithm, that means this is actually the reverse of the power rule. So take it back as that exponent. To clean that up, which will end up giving us what? Yeah, power rule for exponents, x squared raised to the 4th power, you multiply 2 times 4. 2 times 4, of course, is 8. And then what do we do next?
You would combine, because you know it's division, so you just go back, so it'd be log 7 is x over 5 over x over 8.
Okay, which will clean up into
Yeah, x to the negative.
so it should be either 1 over x to the 3rd, right? Since our larger numbers in the denominator. And again, my math lab kind of has its own little quirk. So you will actually need to see how they want you to write the answer. If they're okay, you can leave it as x to the power of -3 with base 7. I'm not sure they're going to want you to bring that -3 in the front, because if you bring the -3 in the front, you're again splitting it up. It's not a single log anymore. So either the 1 over x to the 3rd or x to the -3, you just kind of have to see what my math lab wants. On paper, of course, I'd accept either of those two answers. Either 1 over x to the 3 or x to the -3. Amy? I saw your hand go up.
I was asking about if you bring the -3 to the front.
Yeah, and normally that means you're breaking it apart. So if they want it as a single log, we normally don't bring that -3 to the front. Okay. All right. Again, take a minute and let me see what you come up for 18. Does anybody have an answer? Okay, so the plus sign tells us what rule? And the minus sign?
Division.
Quotient rule. Yeah, so all the ones that are being added will end up giving us,
2x1.
yeah. So you're literally just multiplying because the first 3 are with the addition sign. That's where the product rule comes in. So you're multiplying 2 times x times y, and then now we have the minus log of z, so that will end up giving us,
Log 2xy over z.
yeah. Those guys stay together, and since z was the only one which was the minus log of z, he goes on the denominator. Looks like it should be more complicated, doesn't
It's
it?
like that's like they do that. They throw curveballs right at the end too.
All right, so just a comparison between the exponential and the logarithmic rules. So you can see how the product rule works for each type of functions, quotient rule, power rule, zero exponent rule, I guess. Okay. So as I mentioned, normally our calculators only do base 10 and base E calculations. Now there are some newer calculators which will let you type in a base which might be different, like a base 2, base 7, something like that. So normally what would happen is we would actually need to use the base change formula so that we could rewrite our logarithm into a base 10 or natural log so that we could use our calculators to solve them. So that's kind of where this idea of base change formula comes in. Now, when I actually learned logarithms for the first time, they were actually still using tables because we were not allowed to use calculators. So this is where you would go and see what was the base of your logarithm and then kind of get an approximate value for the, whatever this value might be, and then you would kind of get an approximate answer. Obviously, calculators changed a lot of that process. So as you can see, if we are given 1.03 as our base, raised to the power of x equals 5, we're basically asking ourselves the question, what should that x value be so I get the exact value of 5? Now we can keep trying and experimenting with that x. We're not going to get an exact answer. So normally, we want to convert this into a logarithm where you get log of 5 with base 1.03 equals x. And if I can simplify this, I can get an answer for my x. But again, we have that restriction because I cannot really do a base of 1.03. So we're actually converting it into a base 10 logarithm. So as you can see, we're starting out with our exponential format. We're taking a log on both sides of our equation here. And the reason I'm using log is using that power rule, I can bring that x in front of my logarithm, divide both sides by log of 1.03, and now I can use my calculator to simplify log of 5 divided by log of 1.03, and we're getting an approximate answer of 54.4487. So 1.03 raised to this number will actually end up giving us 5, or at least close enough since this is an approximate answer. So the way the base change formula works, and this is just in general terms, when you have a to the power of x equals m, that m usually goes on the top, so log of m on the top, and log of A on the bottom. Now they're actually using base B here just to keep it general, but for our calculations, our base B will either be base 10 or base E so that we can use one of those two log keys on our calculator. So your general format for the base change formula is the value of the logarithm goes on the top, the original base for the logarithm goes on the bottom. So you have log of m on the top divided by log of a on the bottom. Same thing, it can be natural log of m on the top divided by natural log of a on the bottom. So using this base change formula, and we're rounding it to 4 decimal places, now you can either remember the base change formula which is log of m on the top, log of a on the bottom, and then remember instead of log, you can also use natural log. Okay? If you remember the formula, it definitely makes your life a lot easier because then we can go directly into x equals log of 9 divided by log of 2, and you can come up with your answer. If you don't remember the base change formula, then go the route that the example was going to. So if you have 2 to the x equals 9, go ahead and take a log or a natural log on both sides, doesn't matter. Using the power rule, that x will come down to the base level. And then to get x by itself, divide both sides by log of 2. And you get to the same exact answer, log of 9 divided by log of 2. You can get an approximate answer. So if you don't remember the base change formula, just remember to take a log on both sides. And then using the power rule, bring that x down. So what is this approximate answer?
3.16. Did you say to the
4 decimal places.
so 3.1699?
Okay. Can somebody else verify that number for me? Yeah. So with base change formula, we normally go for 4 decimal places no matter what. Okay, go ahead and do number 20, same exact thing. Let me see what you come up with. So 3.1699 for this guy. To change things up, if you want, you can use a natural log this time. So again, by the base change formula. And if you don't remember that, what does this guy come out to be for number 20?
2.2024.
2.2024, check your rounding again.
2.5.
be very, very careful with those rounding because that's the place where you're going to lose points at. A question on 1920, base change formula. Now the application for base change formula is actually what you're looking at in these next two examples. So where would the base change formula come into play? So looking at 21, and this is the one where they're asking you to round it to the nearest day. So they're saying how long does it take for $100 to grow to $400? And again, 5% compounded daily. So they're using daily compounding here, which means you're actually using the formula with the n as part of it. It has to say compounded continuously if you're going to use the formula with the e in it. So they are saying how long does it take for $100 to grow? So that's our principal. It's growing to $400, so that's our amount. It's growing at a rate of 5% again. So 5% as a decimal. It's compounded daily, which means your interest is being calculated on a daily basis. So daily, remember we use 365 as the number of days in a year. So n will be 365. And time is what we're trying to calculate. And remember, they're asking us to round this to the nearest day, which makes sense because if you're compounding on a daily calculation, then of course we need to know exactly how many days it's going to take for the money to grow from $100 to $400. So plugging this into our formula, you should have 400 equals 100 parentheses 1 plus r, which is 5% over n, and then exponent of n times t, because t is the only value that's missing here. Okay, so we got to be a little careful this time. This whole parentheses is our base, which is raised to the exponent of 365 times t. So the first thing you want to do is get rid of that 100. Since it's 100 multiplied with the parentheses part, we're of course dividing both sides by that 100. So what do we get on the left-hand side? 4. And of course that whole parentheses 1 plus 0.05 over 365 raised to the power of 365t. Point 0.05 divided by 365, is that not really a clean number? I was hoping for something small, but since it's giving you a pretty long decimal, I'm actually going to leave them as they are, okay? Right now, my base is this number, my t, the unknown values in the exponent. So again, this is where our base change formula, or basically logarithms, are coming into play. You can use log or natural log, doesn't matter, whichever one you want to use. Let's just go with logs for this guy. So we'll take a log on both sides of our equation. Okay, and again, we're using log so that we can bring that t down to the base level. So that whole exponent will come down in front of that logarithm. We're trying to get t by itself, which means everything else needs to be divided on the right-hand side. which means I'm dividing by the 365 times log of this whole parentheses here. Same thing on the left-hand side, 365 times. Okay. So basically we've just got t because everything else has been canceled out. Now be careful how you type this into your calculator to simplify the left-hand side. Parentheses will definitely help you keep everything straight. So if you were trying to type this whole left-hand side at one time, of course, start with log of 4. Again, if your calculator opens a parentheses for log, make sure you're closing it at this time. Then divide by, since there are 2 terms in our denominator, again, open parentheses, 365 times log, and again, if it automatically opens parentheses for you, that would be great. If not, open one for yourself. And then 1 plus 0.05 divided by 365. We're closing one parentheses for the log and one parentheses for this one right before the 365. So you should be closing 2 parentheses at the end. If your calculator automatically types it as fractions, you may not have to worry about the parentheses. So it really has to depend on your individual calculator. Some of you guys have the reverse process, right? So if you're doing this in reverse, I would start with the denominator first. I would do 1 plus 0.05 divided by 365. So just do that parentheses part first, get that answer, then hit your log key. Whatever that answer comes out to be, multiplied by 365. If your calculator stores the last answer you calculated, then you should be able to do log of 4 divided by shift or the second key and then answer to get that whole denominator. So it might be a little bit of a trial and error, but looks like for the value of t, it's coming out to be 27 point, oh, I don't have my decimals. Okay. 7278. 7278? Okay. Since they're asking us to round it to the nearest day, we do not want to round these decimals. So this is the nearest day calculation. We know we have 27 years for sure. So start by subtracting that 27 from your calculators first, so that you only have this 0 point and then this decimal, and multiply that decimal by 365. Which is coming out to be 265.64. So what's that, 266 days?
Yeah.
Approximately. And that's gonna be your time. That's how it's gonna take $100 to grow to $400 at 5% interest. Because you know you're growing your money 4 times. That takes a lot of time. So about 27 years and 266 days. Did anybody's calculator not work and did not give you that answer? Okay. So obviously we just have that one example left to talk about, number 22. We'll do this last example. We'll do, what is it, the 4 problems from 4.4, and we're done with chapter 4. So we'll finish chapter 4 and start chapter 5. Probably finish chapter 5 next class. So finish chapter 4, finish chapter 5. And then, as I was telling you, leave you guys with